Today's lecture will focus on the structure of ceramics. So as compared with metals, ceramics are relatively more complex because ceramic crystals are usually composed of at least two elements and often more. So you will have positively charged so-called cations, which are usually metal ions, and negatively charged anions, which are non-metallic ions. So a conventional example is this sodium chloride ceramic crystal, where you have your cation as your sodium ions and your anions as your chloride ions. And this is your crystal structure of your sodium chloride ceramic structure, where you have two interpenetrating FCC structures. The coordination of ceramic crystals will depend on the relative magnitude of your metal and non-metallic atom spacings or radiuses. Okay? So for example, in this most simple binary 1-to-1 ceramic crystals, which means you have one metallic element and one non-metallic elements, and so it's an AX type of ceramics. You may have different crystal structures based on the ratio between your metallic and non-metallic element radii. For example, you may have a sodium chloride structure, which are two interpenetrating FCC structure, and you may have the cesium chloride structure, where you have a simple cubic lattice, or you may have a relatively more complex zinc sulfide structure, where you still have a two interpenetrating FCC structure, but the relative displacement between the two FCC structures is this 1/4 of body diagonal. So we'll see one by one. For example, in this sodium chloride structure, you will have this RC over RA ratio. RC is the ratio or radius of your cation, and RA is your radius of your anion. And this RC over RA ratio has this value which falls into this range, which gives rise to a 6 coordination number. And with the cesium chloride, you will have a different cation to anion radius ratio, which will give rise to a different coordination number, which will result in a different crystal structure. This is exactly the same case for your zinc sulfide, where you have a coordination of 4, which give rise to your two interpenetrating FCC structures with relative displacement of 1/4 of body diagonal. Okay, so now we move on to a relatively more complex situation where you have non-1-to-1 ratio between your metallic and non-metallic elements. For example, in this calcium fluoride ceramic crystal, you will have a simple cubic lattice of your fluoride. So you have a simple cubic lattice of your fluoride ions, and then your coordination number is 8 based on the cation to anion ratio. And your calcium ions, your calcium cations, they will occupy only half of your body centers in a simple cubic lattice of your fluoride. Okay, so this is the AX2 typed ceramic crystal structure, and you can have much more complex ceramic crystal structures in this way. In a more complex case, you may have a ternary ceramic crystal, which means you have 3 elements. Usually you will have 2 metal elements. For example, in this so-called barium titanate, you have 2 types of cations of barium and titanium. Okay? And then the only anion is this oxygen ion. Okay? So you will have this relatively complex ceramic crystal structure where different ions occupy different positions. And this particular crystal is very attractive in terms of optical and magnetic properties. Okay, so to summarize a little bit, even with a simple stoichiometry, you may have different crystal structures based on the difference in their cation to anion atomic radius ratio. And similar to the theoretical density calculation for metal crystals, you can also calculate the theoretical density of your ceramic crystals, for example, you can write down a similar equation of density calculation as this one, and the only difference in comparison with the metal theoretical density calculation is that you must put the total number of formula units or the number of your atom pairs in your ceramic crystal into this position. Okay? And then you just do a summation of all your K-type atomic number and A9 atomic number, and then the volume of the unit cell as well as the Avogadro constant. Okay? This is an example showing the calculation of theoretical density for sodium chloride, where essentially in a unit cell of sodium chloride you have four pairs of sodium and chloride ions. And then if you put these four pairs in the equation together with the atomic mass of your K-types, the atomic mass of your A9s, and then eventually you can calculate the theoretical density of your sodium chloride ceramic crystal. Okay, now a very complex ceramic crystal is the silicate ceramics, where essentially the basic unit is the silicon oxygen tetrahedral. And essentially, all your silicon items, they will form a diamond cubic structure. So here is your diamond cubic structure. You have two interpenetrating FCC structure together with the relatively displacement. Again, it's a 1/4 of body diagonal. So essentially, the solid points corresponds to your silicon items. The silicon items, they form this diamond cubic structure by itself. And each of these silicon items is connected with four oxygen items, okay, forming a silicon oxygen tetrahedral. And this is a really complex structure, but it's an important structure for a lot of applications. And you may have even more complex structure by putting more K-types in. For example, in the so-called kaolinite structure, you have additional K-types of aluminum putting into the simple silicon oxygen tetrahedral. And you end up with a much, much more complex crystal structure for this kaolinite mineral, essentially. So now we have talked about the crystal structure of ceramics. Thank you very much.